Hi, my name is Stan, and today I'll be presenting CytoImageNet, a pre-training dataset for bioimage transfer learning. First, I'd like to begin with our motivation. Automated microscopy allows us to explore biological hypotheses at a large scale. An important component of automated microscopy is feature extraction, where each raw image can be converted into a representation useful in some task, such as classification. And this remains an active area of research. Some have explored the use of transfer learning to perform feature extraction using pre-trained neural networks. To define some terminology, pre-training is the act of training a model as a pretext task. Meanwhile, transfer learning is the reusing of pre-trained neural networks on a different downstream task. In our case, images are passed through pre-trained neural networks, and their intermediate output is extracted. In computer vision, models pre-trained on a subset of ImageNet are commonly reused in downstream image tasks. ImageNet pre-trained features have shown to be useful even on microscopy and medical images, which are not included nor similar to images in ImageNet. We hypothesized that pre-training models on a more domain-relevant dataset will yield more useful features than ImageNet. Pooling together 40 open-source datasets, we present CytoImageNet, a large-scale pre-training dataset of microscopy images with 890,000 images and 894 classes. We highlight two key differences between ImageNet and CytoImageNet. First, CytoImageNet contains grayscale images as opposed to RGB. And second, CytoImageNet labels are derived from experimental metadata. Meanwhile, ImageNet labels are human annotated. 90% of CytoImageNet is used to pre-train EfficientNet B0 models, and the remaining 10% is left for validation. We demonstrate that concatenation of CytoImageNet pre-trained and ImageNet pre-trained features is the new state-of-the-art in bioimage transfer learning. We compare features extracted from a CytoImageNet pre-trained model, an ImageNet pre-trained model, and a randomly initialized model on 3 downstream microscopy classification tasks. Together, these transfer tasks test the performance of these features on different organisms, on fully imaged versus single-cell images, and on 2 different classification problems. Image labels are predicted using a k-nearest neighbors on extracted features. Remarkably, the concatenation of CytoImageNet and ImageNet features show a significant boost in performance over either alone. This suggests that CytoImageNet pre-training learns useful and different image features from ImageNet pre-training. Surprisingly, our CytoImageNet trained features alone do not outperform ImageNet trained features. However, our CytoImageNet trained model yielded useful features despite poor accuracy on the 10% validation set. In fact, nearly half of the labels had no correctly predicted images. Meanwhile, the ImageNet trained EfficientNet B0 achieved a 77% accuracy on its validation set. Recent studies on ImageNet have found that increased validation accuracy is positively correlated to transfer performance. This suggests that improving upon the current CytoImageNet validation accuracy may be an important next step in future work. Future researchers may also consider improving upon the CytoImageNet dataset by adding or filtering down labels and keeping multi-channel images instead of converting to grayscale. We hope that this work may spark interest in the vast amount of rich microscopy data available online, and that our simple framework for curating CytoImageNet may encourage others to create new large-scale datasets from openly available data. Thank you.